So in this case, if you look at the free body diagram of the girl, you only show the forces acting on the girl, right? So the first step in drawing the free body diagram is that you isolate the object of interest. Okay? You say, I'm going to draw the free body diagram of this particular object. In this case, that object happens to be the girl. So imagine drawing a boundary around the girl, okay? And whatever objects cut across the boundary, you need to replace the effective presence of those objects by the forces they exert on the girl. So girl is interacting with how many things? Girl is interacting with car, girl is interacting with ground, and girl is interacting with the earth, right? Those are the three things it's interacting with. So that's the first question you need to ask. Identify the object. What are the other things in its surrounding that it is interacting with? And remember, what is a force? Force is nothing but characterization of an interaction. So now all you need to do is look at those interactions and replace those interactions with the forces that those other objects in the surrounding exert on this, right? Okay, so let's look at it. Girl is pushing on the car. Newton's third law says that car is going to push back on the girl. So you have this force of push pointing in the opposite direction, right? Then you have the reaction from the ground that is pushing the girl up. And remember, normal reactions are always perpendicular to the direction of the surface. So surface is inclined, so the normal direction is perpendicular to that incline, right? So that's the normal reaction on the girl. And notice how I didn't draw the ground. And that's a very commonly made mistake. Students, they also draw the ground and they also show the normal reaction. Well, the whole point of showing the normal reaction is that you're replacing the ground because the ground is exerting this reaction. So you do not draw the ground. Okay, so this is not, free body diagram is not just a pretty picture that you're drawing. It is really something that you will use to do the analysis in the next step. Okay, so normal reaction from the girl and ground is gone, right? Friction force, which way the friction force should point? Well, girl has a tendency to slide down, friction force has to push it up, right? So you have the friction force along the incline, which we are calling F as friction. You have the weight of the girl, mass times gravity, right? Any other forces on the girl? Normal force from? We have that, right? This is the N girl, right? Right here, the normal force, N. That's it, right? These are all the forces. Now, of course, one of the students over there said that, hey, we have friction also between the girl's hands and the car. And that's true, because you don't want the hands to slide. If you wanted to account for that friction force would be pointing either in the upward direction or in the downward direction, but it will be tangent to the back of this car, right? That's how it will be shown. But we are choosing to neglect that. All right, now let's look at the free body diagram of the car. What forces act on the car? Well, we, of course, have the push from the girl in that direction. We have the weight of the car. We are neglecting the friction because the car is not being driven. The engine is not applying any torque. So these wheels are essentially free-rolling wheels, and that's why we are choosing to not show the friction on the wheels. We have the weight of the car, and we have the two normal reactions, right? So since this is a three-dimensional car, of course, so you could say that, hey, if N2 is the reaction force on the two rear wheels, then this will be 2N2, and if N1 is the reaction on one wheel in the front, then this will be 2N1. But in this case, if I show N1 and N2 like this, then I'm essentially saying that, hey, we have half of that on each of the front wheels. Okay, so why is the force of friction on the girl going up the incline? So the rule is that the job of the friction force is to prevent the sliding, right? So if the girl were to slide, which way would she slide? Is she going to slide up? No, she's going to slide down, right? So the friction force job is to oppose that sliding, and that's why friction force has to point up, right? So you just look at the sliding, and that tells you which way the friction force should point, right? Another important piece of information in this slide is that you always have to show the coordinate system, okay? And you know, these are matters of habit. This will be needed. If you don't draw the coordinate system, we will not know how you are going to show these forces or how you're going to write these forces when you finally write some of the forces equation or some of the moment equation. So you always have to show the coordinate system. And notice how I've chosen my x direction to be direction along the incline. It is not pointing in the horizontal direction. Why? Because both the girl and the car are going to be traveling along the incline. So I'm just going to make my x-axis to be along the incline, because then I don't have to worry about any movement in the y direction. On the other hand, if I showed my x direction to be this way and y direction to be that way, then I have to resolve all the forces along x and y direction. And why do I want to make my life difficult when I can make it easier? Right? Okay, so that's good. Now, what about the free body diagram of the whole thing? We can always draw a free body diagram of more than one object, the car and the girl together. What about the free body diagram of the girl and the car together? What forces would be acting on both of them together? If I identified my interest, object of interest as both of them together, what are the forces acting on the system? mg, we still have the gravitational pull, right? So we'll have the weight of the girl, weight of the car. Friction force between the girl and the ground, right? Normal force, both n girl and 2 would be pointing. What about F push? What about this push, this force? That will not be shown for the system, right? Because that's an internal force now. There is a force of friction on the girl, right? Is that what you were asking? Absolutely. So the car is exerting the same force F push in the backward direction, right? I don't know if that's what you're asking.
Yes.
Okay. Yes, sorry. Go ahead.
If that's a free body diagram,
Yeah.
and you're accounting for the car as a point, why do you have two normal forces?
On these two? Oh, good question. That's an excellent question. So why do we have two different normal reactions? If I'm going to regard it as a particle, do I need to have two normal reactions? No. If I'm going to regard it as a particle, then I'm not going to need it, right? There'll be just one normal reaction. But if I treat it as a rigid body object, then I could potentially have two separate normal reactions, right? In what situation those two normal reactions be same? When it's symmetric, right? So if the center of mass of this car is right over here, and both n1 and n2 are equidistant from that center of mass, then there will be no reason to assume that n1 and n2 are actually different from each other. In fact, you could start by assuming that they were different from each other, but you will finally get that they're the same. Does that answer your question? Yeah.
Just because I want to make sure I heard you right, you're saying in that picture, like N1 is the force on like the two front wheels?
On the two front wheels, right? Yeah. 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 And in general, they may not be same. If you regard them as particles, then there would be no two reactions. It will be just one reaction, right? But if you regard it as a physical object, which is a rigid body, then of course you could have two different reactions, right? So you can see, right, in this example, we have a situation where we regarded the girl as a particle, but the car as a rigid body. If I wanted to regard the girl also as a rigid body, then I could probably show the normal reaction on both the feet separately, right? Right now I have just one because I'm regarding it as a particle. But if you have 2 feet away from each other, then you could draw the normal reaction on both of them, and they both could be different from each other, right? Yes?
When you push the car, the wheel will rotate, so why we are ignoring the moment of inertia on the wheels?
We're not neglecting the moment of inertia of the wheel. It's just that there is no friction force on the wheel because there is no...
I understand there is no friction, but
Right.
there is a moment of inertia on the wheels, right?
Right.
But we are not showing in the free body diagram any moment of inertia.
The moment of inertia, okay, so we're sort of ahead of us right now. Moment of inertia is like a moment, is like the mass quantity, right? So moment of inertia, if you want to relate with the torque, it's torque equal to moment of inertia times alpha. If there's no torque, it doesn't matter whether you have moment of inertia or not. Your angular acceleration would be 0. We can talk about this. This is not relevant to discussion right now. We can talk about that after the class. Okay? All right, so this is good. So we understand how to draw free body diagram, right? There could be a different normal force, yes. Yeah. So for example, I'm standing over here, right? Let's say I'm standing over here. I have 2 legs, right? I'm standing like this. I could stand like this. Is my normal reaction different on both the feet? Of course it is, right? If I treat myself as a particle, a single point with the mass of whatever mass I have, then I will just show one normal reaction. But depending on how I stand, I could have a normal reaction, right?